All right, so 20. This is a calculus one. So a certain one-dimensional conservative force, it's probably going to be spring force or gravitational force, something restorative force, is given a function of x by the expression of f equals, I'm just going to rewrite this. So f is a function of x equals negative kx cubed. Okay, where f is in newtons, x is, they give you all the units. Okay, yay. A possible potential energy for this force is. Now, if you look at the equation sheet, you'll see, well, first of all, you should know that by the work energy theorem, work is a change in energy, I guess this case potential energy. Now, you'll also notice that work can equal the integral or the antiderivative, however you want to say it, of force dot dx. It might say dr, I don't remember. It's changing position. You get it, hopefully. Okay. Don't have to worry about the dot product because I don't see any indication that it's at an angle. Just treat it like it's flat or whatever. Okay, so anyway, that means therefore U will equal, just do the opposite of, on this, what we did before. I'm going to take this over here, and I'm going to do the opposite power rule thing. So instead of like multiplying and subtracting, what I'm going to do is, and do this in a different color, I'm going to add 1 to this side. And if you're in calculus, you can fast forward. This is for the people who aren't in calculus. So we're going to end up with something that is x to the 4th. All right. And then we're going to divide by this new number, so everything's going to get divided by 4. So it's going to be kx to the 4th over 4. All right. And there is a negative. However, remember this, what you're ending up solving for is potential energy, which is a scalar, so you just ignore that. All right. So let me rewrite this in a way that looks like they wrote it. So this would be 1/4. Remember, no negative because it's energy. 1/4 kx to the 4th. Do we have that? Yes, we do. It's D. That's the answer. Okay. So now let's look at this. Which of the following is a differential equation? Yes, that's calculus. It's not as bad as you think. That correctly describes Newton's second law for a simple harmonic oscillator of mass m and restoring force k. Well, let's see. A harmonic oscillator that has a mass that matters and has k, guess what that is? That is a mass on a spring. Now, if you remember, it says restoring force, right? Yeah, restoring force. Guess what the restoring force on that is? It is your spring force, and that is by Hooke's law, kx, negative kx. All right. Depends on the frame of reference, but yeah, basically, there, you could just do that. All right, so, oh, yeah, like the one above it, a little bit. Anyway, so, and then Newton's second law, of course, says mass times acceleration. So it'll be mass times acceleration equals negative kx. Because, yeah, let's just go with the frame of reference they use on the equation sheet, which would be negative right there. All right, so mass times acceleration equals negative kx. Now, they want a differential equation. So you can write mass times acceleration as either mass times change in velocity over change in time. Or if you recall, this could also be the first derivative of velocity is a change in time, or the second derivative of position with respect to time. That's a change in time. I'm going to respect for time up there. One of these. Okay, so let's look and see. Well, that's not negative kx, so that one has to go away. I think that's it, but let's double check. That says kv, even though this part's right, so nope. Okay, that says kx equals, that says that equals momentum because that is dx dt. And then not that. Okay, so yeah, it's B. The answer to 21 is B.